Hello everyone and welcome back to the Kohi Game Engine series. Today we're going to tackle the Vulkan Allocator. So, last time we tackled the memory alignment, and I've mentioned several times that that is a requirement for the Vulkan Allocator. And so, what do I mean by the Vulkan Allocator? So, if we go into our Vulkan backend, and we go into initialize. Whoops, wrong one. Initialize, backend initialize. We have a to-do item here with a comment of custom allocator. And we're setting our context allocator to 0, and we've been sort of just passing this around and using it anytime that we are creating Vulkan resources of any kind. And so what Vulkan actually allows you to do is it allows you to provide a allocator, a custom allocator, that the driver can then use to reach out to say, hey, give me some memory. And you can provide one that does that and provides it with the memory that it needs. But there are several requirements that must be met. But before I get into those, why would you want to do this? And how does it work currently since we actually don't have an allocator, right? We're passing 0 here, which is essentially null. Right, allocator, for those of you who don't recall, this was a while ago, we have this VK allocation callbacks pointer, which we're nulling out. So one of the biggest reasons we want to do this is for reporting purposes, so that we know how much memory we're using, and so that we have a little bit of control over how that memory is allocated. Right now, since we're passing null to the allocator, essentially passing null to the allocator every time we create resources, we are saying use whatever the driver provides. And that basically reaches out under the hood and obtains its own memory and allocates that from the OS, which for a lot of intents and purposes is just fine, but for our purposes, we actually want to go ahead and wrangle control of that. Now, there are existing libraries out there that you can use for this that are going to be definitely more robust than what we're going to implement in this video. Basically, what we're doing in this video is tying that in with our allocation system, but we're basically not maintaining absolute control over everything. At least not yet. So we're going to start off implementing a very simple allocator that basically just ties into our memory functions that we just implemented in the last video, and doesn't really do much else aside from the reporting aspect of it. And then we'll get into optimizations later. We're also going to provide the ability to turn this on and off, so that if we run into a problem with it, or if we determine that maybe the one that comes with the driver is a little bit quicker, and maybe we only want to use this for debug purposes, we can turn it on and off at will. And so with all that in mind, we're going to go ahead and take a look at that. However, before we do that, there is one minor thing that I would like to address, and that is in our startup routines. So one of the things that we're doing right now is we are, when we're creating our Vulkan instance, we're gathering up our required extensions, and then we gather up our validation layer names that we want to use if we're in debug mode. We go ahead and we are actually performing some validation that those validation layers actually exist that we're requiring. And if they don't, we report on it. Otherwise, we report that they exist. But we're only doing that for the validation layers. We're not actually doing that for the extensions. And so if we ever wind up in a situation where we're requesting an extension that we want to require, but the system doesn't have it, we're not going to have any way of knowing that, other than the fact that it's just going to basically quit out with an error saying, hey, we're missing an extension, but it's not going to tell us which one. So I want to add a little bit of enhancement to the extensions section of code to do some reporting on that. And so the way that we're going to do that, and I'm going to, just to keep this brief, I'm going to sort of just paste in some code here. So after we have gone ahead and set the extension names, we're going to go ahead and verify that everything exists. So we're going to follow our pattern of getting a count and then an array of those individual extensions. So we're going to look at the available extension count, and we're going to get the count of that by calling vk enumerate instance extension properties. The layer name we're going to pass as null because we're not wanting to filter this by a specific layer. We are going to pass in a pointer to property count, which is the address of available extension count, and then we are going to pass 0 or null for the properties array. So this is going to give us the count, and then we'll use that count to do a darray reserve to get available extensions to reserve that space, and then we'll go ahead and populate that with another call to vk enumerate extension properties, this time passing available extensions. So that's going to give us the list of extensions that are actually available. The next thing we're going to do is similar to what we do below. We are going to loop through each one of our required extensions. So in this case, that is length. I'm actually going to change this to required extension count to make it a little bit more explicit as to what that is. And we're going to go ahead and loop through each one of those and then check through our available extension count. And if we find it, we're going to go ahead and say we found it. If we don't find it, then we're going to throw a fatal error saying required extension is missing, spitting out the extension name. So this will be a little bit, just give us a little bit more information if we ever run into a problem with that. One other small change that I want to make is down here in this section where we are looping through the validation layers. Currently what we're doing is we are saying we're searching for the layer, and then if we find it, we say found, and that just takes up 2 lines for each individual layer, and that's kind of wasteful. So I'm just going to clean this up a bit by removing that first message and moving it in here to say we'll say found validation layer, and we'll spit out the layer name there. And then, of course, the fatal will remain the same. Obviously, we have some cleanup here to do because we have done this for the available layers, but not the extensions. So we'll say here, available extensions, and we'll clean up that memory there. And so that will just give us a little bit better capability to debug. The other thing we're doing is on the create instance, we're just doing a vk check, and I actually want to utils. I actually want to use our Vulkan result is success and our Vulkan result string. And so to do that, do I have these included? It does not look like I do. It's actually, oh yes, I do. It's right there. Okay, I was going to say that's surprising I don't have that included, but I do. So instead of calling create instance here and just passing that to a vk check, we want to be a little bit more verbose with our check. So I'm going to say vk result instance result, and we'll set that to that. And then we'll say if not Vulkan result is success, and we'll pass through instance result. So if that fails, we will go ahead and report on it. So we'll say Vulkan result string, and let's see, do we need to pass in? No, it looks like it gives us a string already. Let me see if that dynamically allocates that or not. I think it does. Actually, it does not. It returns to us a constant. Okay, so that's not dynamically allocated, so we don't have to worry about it being cleaned up. So we'll just pass through the instance result to that. We do want to get the extended information from it. So we'll say constant character array result string, and we will do a k fatal, and we'll say Vulkan instance creation failed, and actually we'll say with result, and we will surround that result with single quotes and pass in result, comma, not period, result string. And we'll go ahead and see, this is I think this is a Boolean, right? Yeah, we'll go ahead and return false. Okay, so this just makes it a little bit more verbose if we have a failure as to what actually failed. Okay, so that is the first enhancement that I wanted to kind of put in place. Okay, so the next thing that we need to do is we need to talk about our Vulkan allocator. So we will just pull up my notes here. So if we go ahead and let me just grab a new browser window here. And we want VK allocation callbacks. We'll go ahead and search for that and have a look at the spec. So VK allocation callbacks is essentially a structure with a bunch of function pointers. So we can store some sort of free-form user data in here if we want to, which we may or may not wind up using that. We have a function for when allocations take place, a function for when reallocations take place, a function for when frees take place, and then we have an internal allocation notification and internal free notification. So if we have a look here, the p user data is a value to be interpreted by the implementation of the callbacks. When any of the callbacks in this are called, the Vulkan implementation will pass this value as the first parameter of the callback. So this is definitely going to be useful to us at some point. This value can vary each time an allocator is passed into a command, even when the same object takes an allocator in multiple commands. And then we have our allocation function, which is an application-defined memory allocation function. So we're just going to point that to our allocation function. We have a reallocation function, which essentially is just going to be a free in an allocation in our case. And then we have a free, which is a application-defined memory free function. And then we have the internal allocation and free, and these are a little bit different. So these are application-defined functions that's called by the implementation when the implementation makes internal allocations. So this is internal allocations to the Vulkan implementation, aka the driver. We have no control over that, but we do have the ability to get reports on when those allocations take place, so that we can still actually have an idea of when those allocations are made, so we can still sort of track the total memory usage even if we don't have control over it. That being said, any of these can be null. They all can be null, but some of them, if they are not null, have specific requirements. So if it's not null, allocation, reallocation, and free must point to a valid user-defined pointer function. And then specific for the internal allocation functions, if either the internal allocation or internal free is not null, then both must be valid callbacks. So we're going to be filling in all of these, okay? And we're basically going to go through and look at these one by one. So the user data is pretty self-explanatory. The VK allocation function, if we click into that, so we have our p user data as the first property, as it mentioned. We have the size of the allocation, the alignment, and the allocation scope. Now, allocation scope is not something that we are going to be paying attention to right away, but eventually we are going to be paying attention to that. So right now I'm just going to kind of ignore it and just pass all of this through, specifically our size and alignment to our allocation routines. And if you guys recall the previous video, this signature will look somewhat familiar because we're talking about the size and alignment. So this is one of the reasons that we had to implement that stuff in the last video, is to support this. So the size is the number of bytes of the requested allocation, and then the alignment is the requested alignment of the allocation in bytes and must be a power of 2. And certain functions will call for different alignments. Sometimes they'll be, like an 8-byte or a 16-byte allocation. I've seen 1024 before, so there's all these different requirements for alignment. So our function has to be very flexible in terms of what alignment is actually passed through. So our description, in this case, if the pointer function is unable to allocate the requested memory, it must return null. So in other words, if we fail for any reason, we can't just abort out of it. We have to return null. Otherwise, it has to return a valid pointer to a memory allocation containing at least size and bytes, and where the pointer value is being a multiple of alignment. So we just need to make sure that that address is aligned. Okay. So let's see. Correct Vulkan operation cannot be assumed if the allocation does not follow these rules. For example, PFN allocation or reallocation could cause termination of running Vulkan instances on a failed allocation for debugging purposes, either directly or indirectly. In these circumstances, it cannot be assumed that any part of the affected VK instance objects are going to operate correctly, even destroying the instance, and the application must ensure it cleans up properly via other means, e.g. process termination. So basically, if these allocation routines fail for any reason to actually provide valid returns, it can screw things up to the point where the only way to actually come back out of it is to basically kill the entire process and start over. So we need to be very careful in our implementation here to make sure this is absolutely right. If it returns null and the implementation is unable to continue processing the current command without the requested allocation, it must treat this as a runtime error and generate VK error out of host memory at the appropriate time for the command as described in return codes. And this is basically just saying that that is what the driver has to do. So the driver is responsible for making sure that this is done correctly. If the implementation is able to continue correct processing of the current command without the requested allocation, then it may do so and must not generate this error. Again, this is specific that what the driver must do, so you know that this is going to be the result of that. And that is pretty much it. And then these other functions are defined in a very similar way. So if we take a look at reallocation, it pretty much has very similar requirements, only it takes in the obviously the user data, the original pointer, the size and alignment, and then the allocation scope, and returns a potentially new pointer. And it says P original must either be null or a pointer previously returned by reallocation or PFN allocation. So in other words, we can't allocate memory from one of our allocate routines and then pass it into this reallocation. That it's not going to guarantee proper functionality. It has to have come from one of these two pointer functions. Size is the same thing. Alignment is the same thing. Allocation scope, again, we will get back into that in a bit. So PFN reallocation must return an allocation with enough space, bytes, same as before. And the contents of the original location from bytes 0 to min, original size, new size, -1, must be preserved in the returned allocation. So in other words, it's saying essentially when you are reallocating the memory, it's assumed that you are keeping the old memory and adding on to it. So if your size is larger than the old size, then the contents of the additional space are undefined. Otherwise, the bytes before in the original amount of bytes should be preserved. If satisfying these requirements involves creating a new allocation, then the old allocation should be freed. We are going to be doing that to ensure that that allocation winds up getting freed. If p-original is null, meaning that we call reallocation and there is no previous allocation, then it must behave equivalently as if we called reallocation with the same parameter values, obviously without the original. So we need to basically just treat it like a brand new allocation. If the size is 0, then the reallocation must behave equivalently to call free function with the same user data parameter value and p-memory equal to p-original. Now this, I feel like this might be a bug in the documentation, because if we're calling reallocation, then why would it behave equivalently to free? What is the behavior here? Non-null must be a pointer. Application should free this memory. But this is a return type of null. So it can't behave equivalently. I think this is supposed to be pfn vk allocate function. I think that's a bug in the documentation. I'll have to look into that. I think that's wrong. Anyway, if p-original is not null, then the implementation must ensure that the alignment is equal to the alignment used originally to allocate p-original. So basically what this is saying is when we pass in p-original, the alignment here that's passed in cannot be different. So we actually need to validate that the original allocation's alignment is the same as this alignment and boot out as a non-successful allocation if that's the case. So if this function fails and p-original is non-null, then the application must not free the old allocation. So we need to make sure that we take that into account as well. And then it must follow the same rules for return values as allocation function. And then the last two, let's see, or actually, no, did we already go over? Yeah, we already went over free function. Yeah, so the last two, we have internal allocation notification, which is this guy. So basically all this is it just tells us the size of the requested allocation, the allocation type, and the scope. And then, as I've mentioned before, this is purely an informational callback. So it's purely for us to track it, but it doesn't really allow us to do anything. Same is true with the internal free notification. Again, this is purely informational. So it passes through the size, the allocation type, and scope. And actually, it doesn't say it's purely informational on this page for some reason, but it is. So these are what we're going to be setting up. Okay. And we've gone over the valid usage. So now that we have an understanding of what we need to implement, now we're going to actually start our implementation. So let's go to the top of Vulkan backend. And actually, we're going to be working, I believe, exclusively in this file. There are actually some other changes we're going to have to make, but I'm going to close the other ones for right now. Okay, so we'll go all the way here to the top, and go to initialize here. And in fact, actually, even before we go to initialize, let's go at the top, because I want to actually, I want to get some things sort of set up and defined. So right here after our includes, but before we actually start declaring stuff, I actually want to include a few macros. So I am actually going to enable this. So we're going to have Vulkan Allocator trace. We're going to set that to 1. So this is for us to be able to trace allocations. I'm not going to leave this on because this is going to basically spam our console with our Vulkan Allocator allocations. And so I'm going to turn this on for now so that we can see it in action, but I'm not going to leave it on. Next, I'm going to set up another switch for whether or not we want to actually use our custom allocator. So that's going to be Vulkan use custom allocator. Again, I'm going to set that to 1. If we want to disable it, we can just comment this whole thing out or set it to 0. And next, we'll actually come down and we'll probably go after these function definitions. We'll put it right here before. Yeah, we'll go right in between where we actually are for declaring these and our private functions. We'll put it right here. So we'll include, or we'll say if Vulkan use custom allocator equals 1, and then we'll go ahead and put all of our function definitions within here. And basically what we're going to do is if we have the custom allocator turned on, we'll go ahead and compile these in. If it's turned off, then we won't even bother compiling it. And that will be eventually hooked to debug or trace builds. And we'll eventually have that set up in such a way where depending on what flags we pass to our build process, it will either include or not include these. So the first one that we're actually going to wind up creating is going to be our allocation routine. So I'm just going to paste in the definition, or the function signature rather, of our allocation routine. And what I'm going to do is I'm actually going to include a link here to the spec, just so that in case we wind up forgetting how this is supposed to work in 6 months, we can actually have a resource to look at. So this is our implementation of pointer function VK allocation function. So for the record, that is this guy. Okay, so we're going to implement this one first. So the first thing that it said is if the size equals 0, we must return null. So obviously that's going to be the first thing that we should definitely check. The next thing that we're going to do is we are going to go ahead and perform an aligned allocation of the size and alignment that are passed. So we're going to go ahead and say result is a void pointer. We're going to allocate aligned, passing through the size, the alignment that is passed through. It's passed through as a size t. We're just going to cast that to U16 because we're not going to need anything bigger than that. And then a memory tag of Vulkan. And then we're going to go ahead and set up an if-def here for some tracing information. So if our Vulkan allocator trace is turned on, we're going to ktrace. We're going to say allocated block, and we're going to output the address of that block. We could probably also put, let's actually enhance this. So we'll say size alignment. Actually, we'll just say size equals, and we'll put in LLU, and then alignment equals half an unsigned. Okay, and then we'll say size and alignment. We'll cast that to a U16. Actually, you know what? Let's not cast that. We'll keep it the 64-bit number for now. At least in the trace, okay? So if we have our trace turned on, we'll go ahead and do that. And then here we will say return result. Okay? And obviously we could just return this, but then we kill the ability to go ahead and print that out if we are doing a trace. So that's why we've separated this out this way. And that is all there is to the allocation routine. It's actually, it's dirt simple. So because of all the work that we did in our allocator, there's not a whole heck of a lot of logic that has to be implemented for this. Okay, so we have a line. Let's go ahead and do free next. So we have our Vulkan alloc free. So if we do not have memory, which is the second property, right? So this is the VK free function. If we have a void pointer for memory, then we're going to trace a message saying this block is null, nothing to free, and we're going to output this anyways. That's always going to be 0 if that's the case, but we're just going to output that. And then once again, if we have trace turned on, but we've passed this test, then we're going to say, okay, well, now we're going to attempt to free the block at that address. And the next thing we're going to do is we're going to use our new logic to obtain the size and alignment of that allocation. So we'll pass through the memory block and obtain the size and alignment. And if we actually have a success, then what we're going to do is we'll go ahead and trace again. We'll say the block at this address was found at the size alignment, spit that out, and then freeing align block. And then we call kfree aligned, passing in the memory block, the size, the alignment, and of course memory tag Vulkan so that it gets freed under the proper tag. If this, for some reason, fails to obtain that, then we actually are going to go ahead and output an error message saying that the Vulkan allocator failed to get an alignment lookup for the block at this address. And that'll give us a little bit of information in terms of how we want to go ahead and handle that. Okay, so the next thing that we're going to want to do is handle the reallocation function. So I'm going to paste in the function signature for that. So again, this is the implementation of PFN VK reallocation function. So we have our user data, the original pointer, the size, the alignment, and the allocation scope. And so if the original pointer is null, then what we're going to do is we're going to pass this through to Vulkan allocation, and we're just going to return the result of that because it basically should just perform a new allocation at that point. So if we call reallocation and we don't have another pointer to copy memory from, then it becomes super easy. Likewise, we're also going to check to see if the size is 0, then we're going to return null. This may or may not catch that. If we do have an original pointer, but we pass 0 for the size, we need to catch that here. And the next thing that we're going to do is go ahead and get the size alignment for that allocation. So basically, if the P original is not null, then we have to use the same alignment for the new allocation as the original. So we go ahead and we get the size and alignment for that. If for some reason that fails, then we're just going to say reallocation of unaligned block and then the address. And then obviously if we are tracing, we are going to output a trace message just saying we're trying to reallocate the block at that address. And then what we're going to do is, in our case, we're not actually going to do a realloc because we don't have realloc within our K memory. But all that ultimately is we are calling for a new allocation. And then if we have the result, we're going to go ahead and say we are reallocating the block original to this new address. And then we're simply going to copy over the memory. So that is here. Okay. In fact, did I? Yeah. Okay. I'm missing the closing bracket here for that function. Yeah. Okay. Let's see. Okay. So after we have the new allocation, we'll copy over the original memory. And then we'll go ahead and, again, if we're tracing, we're going to go ahead and say we're freeing the original block, and we'll do that here, right? And that is obviously only only if the new allocation was successful. In fact, let's see. This should all be, let's see. That should only happen if we have an original. So if there's no, right. So if there's no original, then we would have gone through this. Right, okay. Just making sure that we didn't miss a case there. Okay, so we would have freed the original memory, but only if the new allocation was successful. So if we, for example, did not have a successful result, all of this actually should be in here. There we go. So only if we have a successful allocation do we copy over the original memory and free the original memory, right? If we fail this, then that's a separate story. Let's see. So if we do not have a result, let's actually put another if def in here. And if, and we'll do care fail to realloc original. Okay, so if for some reason we actually fail to allocate new memory, we're going to go ahead and bleat about it here. And then either way, whether we're successful or not, we will return, the result. Okay? So basically, if we do not have an original, we proceed as a normal allocation. If we do have an original, we do some verification, get the size and alignment of the original, and use that instead. We probably ought to do some sanity checking on this alignment that's passed in versus the original alignment. So I'm actually going to say, in fact, if this is not aligned, this should be return 0 here. Let's see. So I'm going to add another check to say if alloc alignment is not equal to alignment, and then I'll say k-error attempted realloc using a different alignment of LOU than the original of HU. And we'll say alignment and then alloc alignment and return 0. So we'll do a little bit of sanity checking here to make sure that the alloc of the original, the alignment of the original allocation matches the alignment that we're requesting, because that is one of the rules that we have to abide by. Okay. So that is pretty much all we need to do for the reallocation, at least for now. So the next thing that we're going to do is implement the internal alloc. So right at the end of this, this is the purely informational report of an allocation. So all we're going to do here is use our new reporting functions. So we're going to trace, if necessary, internal allocation, external allocation of size, And then we will, since we don't actually get a pointer to that, we have no idea what address it is. All we're told is the size. And then we'll call kallocate report, passing through the size, and a memory tag, this time of Vulkan external. And that's it. That's all we can really do with that. And so likewise, we have the internal free, which is the same thing except for free. So we have the external free of size, and then we free report with the memory tag of Vulkan external. Okay. Next, we actually need a quick little utility method to set up the Vulkan allocator for us. So we are going to have a method called create Vulkan allocator. And it's going to take a pointer to the allocation callback structure that it's going to be populating. And so we're going to check if callbacks. And if we have a pointer, we'll ultimately return true. If we do not, then we're going to return false. And basically the true indicates success, otherwise false. And there really should be no reason for this to ever fail, because all we're doing is passing a pointer through. But here's how we're going to set that up. So we're going to set the PFN allocation to Vulkan allocation, reallocation to alloc reallocation, free to free, internal alloc to internal alloc, internal free to internal free. And then for the P user data, we're actually going to set this up to be the address of context, which is going to be up here, our static guy right there. Okay, so we're not going to need that yet, but eventually we are probably going to require that. So for now, that's going to be our context is going to be what lives in P user data. So any of these are going to just be cold castable to our context. Okay, so that is create Vulkan allocator. And that is all there is to the allocator for right now, the custom allocator. So I'm actually just going to put in a comment right here as to what this endif is for, because it's kind of long. And I'm going to come down here to our to-do for our custom allocator. And I'm actually going to change this to note, because it's no longer to-do. We actually have it. And we're going to fill this out. So we're going to say, first and foremost, if Vulkan use custom allocator equals 1, then we're going to have an else statement and an endif. So basically, if we are not using the custom allocator, we are still going to set it to null. If we are using a custom allocator, then we need to do context allocator equals, and we're going to kallocate the size of vk allocation callbacks with a mem tag of renderer. We could technically use Vulkan for that, but I'm reserving Vulkan for Vulkan specific allocations. And so now we have some actual memory allocated for our allocation. And then we'll say if not create Vulkan allocator, and we're going to pass the address of context allocator. Actually, not the address, just the allocator itself, because that's already a pointer. Then we'll say fatal, and failed to create Vulkan allocator, custom Vulkan allocator. And we will return false for now, anyways, because we're going to treat that as a hard stop error. I suppose we could just null it out. Let's do that, actually. Continuing using the drivers default allocator. And instead of returning false, let's do kfree context.allocator size of vk allocation callbacks, and then mem tag renderer, and we will copy this line of code and put it up here. If this fails, gracefully fall back to the default allocator. Okay. So, I mean, it's not great that we're doing an immediate free and allocate here, but I'm not really that worried about it. I think that will be just fine. I don't think this should ever happen anyways, but if it ever does, at least we've caught it, and it doesn't bork our entire engine. It can at least fall back and deal with it. So that's actually a little bit more robust than what I was thinking. So now that we have this, we can actually go to our shut down, and all the way at the end, because we're going to want to destroy this last surface right after we destroy the instance. We're going to destroy the allocator callbacks if set. So we'll say if context.allocator, and again we'll call kfree context.allocator, allocator size of vk allocation callbacks, mem tag renderer, and then context.allocator equals 0. Okay. And I believe that is actually it. So let's go ahead and clean and rebuild. And we're going to go ahead and launch. And you'll notice all the spam here for all the allocations that are happening. And we'll note that this is actually happening every frame because there's stuff that's being done every single frame. So obviously, you don't want this tracing left on for a very long time, right? You only really want to use that when you absolutely have to. Because if we look at the console.log, this guy is pretty long. So it will help if you actually have some debugging to do, where you really need to know that information. You can see what allocations were done, what address the allocated blocks were made to, and so forth, and where the frees were done. It provides you that information just so you have that visibility, but you're really not going to want to leave this on because it's just not going to be completely necessary to have that logging constantly. So what we actually want to do is go back up here, and I'm going to turn trace off so that we can get rid of that spam. And just rebuild and run. And now, once we are started up, if I go ahead and hit M, we can see here that we are using 2.68 megabytes of GPU memory. And we can go ahead and actually load up some more data. And now that that's loaded, we'll hit M again. And we see that we're at 2.18 or 2.81. So there are a lot of things here that are not being reported. A lot of our data that we're loading, such as our our textures and our buffers, all that stuff is not actually being reported. So let's go ahead and change that. So the first thing I'm going to start with, I think, is actually going to be the buffer, because that is probably going to be the quicker one. So we'll say Vulkan buffer.c. And actually we need to modify the types first. So let's actually go to Vulkan types, and we'll go to Vulkan buffer. And we just need to add a property here. So one thing that we need to do is we need a way to track the memory of this particular buffer. So right under here we have the device memory. We're also going to keep a copy of the memory requirements. That way, if we ever resize the buffer, we don't have to re-obtain that. We actually already have it saved off. So we're going to need that. And then I'm also going to look at the Vulkan image. And this needs two things actually added. So we already have the handle, the memory, the view, but we also need the memory requirements here, and we need the memory property flags as well. So we'll go ahead and track those. And I think that's actually it for the Vulkan types. So we're done with that. And in Vulkan buffer, there are a few changes that we need to go ahead and make. So the first one is going to be in create. So where we are gathering the memory requirements, instead of saving off the requirements here locally, we're going to get rid of that. And we are going to instead save this to out buffer memory requirements. And I'm just going to copy this. And we'll say instead of requirements here, out buffer memory requirements, and down here as well. And then right down at the bottom, probably right after we allocate the memory, we'll go ahead and report it. So the first thing that we're going to do is we're going to check the flags to see if it is device memory that we're allocating against or not. So we're going to say, does the memory property flags include memory property device local bit, right? So if it includes that bit, then we're using local device memory. And if we are, then we're going to go ahead and report its usage accordingly. So if it's device memory, we're going to call kallocate report and pass through the memory tag of GPU local. Otherwise, we're going to tag it as Vulkan. Okay. And that should be sufficient for now, I think, in terms of reporting. If we want to get a little bit more granular with it, it'd be easy enough to come back and adjust that. The next thing that we need to do is in the destruction, we actually need to report the free of the memory. So again, we're basically just going to do the exact same thing that we did before, where we go ahead and determine whether or not it's device memory by looking at the device local bit. And then based on that, it frees it out of the GPU local or memory tag Vulkan category. And then it goes ahead, we're also zero out the memory requirements just to make sure that that field is zeroed out as well, since we added that. And in terms of the buffer resize, we actually need to kind of do the same thing again to make sure that the amount is recorded correctly. So let's see, right when we go ahead and set the new properties, so we've already done the allocation of the new and freeing of the old. Here's where we're going to report on that. So again, we check to see if it is device local memory, and we report the free of that into the correct category. We go ahead and save over the memory requirements to requirements, or we set requirements. We copy, rather, requirements to memory requirements. And then we go ahead and report the new allocation. All right. And I believe that is all we need to do for the buffer. So not a whole heck of a lot of changes, but at least now it will be reporting its memory usage correctly. And so that's one of the reasons, another one of the reasons we wanted these report methods, because it's a different set of memory than coming out of our local device memory potentially. And so we want to report that accordingly. Okay, so the next thing that we need to do is Vulkan image, because this is another space where we're using memory. And so what we'll need to do is right when we're setting the out image width and height, we will need to set the memory flags. And we'll need to set that to the passed in memory flags, just so that we have a copy of that for later. And then when we get the image memory requirements, instead of saving the memory requirements locally, we are going to save that to the out image memory requirements. And that should basically give us what we need there. So this will also have to be out image memory requirements, and I'm actually just going to copy this, change this as well. So that's no longer a just a stored local variable. It's actually stored as part of the image. Now we'll need to report the memory as in use. So once we've allocated and bound, then we're going to again check to see if it's device memory. And then report it to, if it is, as GPU local, otherwise memory tag Vulkan, and we will report that allocation. And of course, since we have done that in our create, we are actually going to need to also come into our destroy, and at the very end of that, report that memory free. So again, we just check to see if it's device memory, report the free, and then zero out the memory requirements. So we'll go ahead and clean and rebuild. Let's see, what did I do here? Oh my, okay. That should be this. Typed a question mark instead of a greater than symbol. Okay. All right, so let's go ahead and run this. Okay, and we'll go ahead and have a look at the reported memory. So we'll go ahead and hit M. And now we see that our Vulkan memory is reported as 2.68 megs, but that we have 199 megs worth of GPU local space being reported. And that is seems like a lot, but that, bear in mind, is the size of our vertex and index buffers as well is also included in that, as well as all the textures we've uploaded. So it's actually not as much as it sounds like because we have allocated those huge buffers, but they're not all necessarily in use. So if we go ahead and load this and do it again, now we will see that we are actually allocating that we actually have allocated, rather, 919 megabytes, basically, of data. So we have some interesting reporting on all of that. So if we look here, before we had 2.68 megabytes of Vulkan memory, and if we come down here, we've got a little bit more at 2.81. So that is, at least for now, our Vulkan allocator. We are eventually going to be making it quite a bit smarter than it is currently. We eventually are going to have it be responsible for all management of memory, and we're basically going to combine all of our memory into one huge block and just let the allocator sort of dole out that memory as it sees fit. But for right now, we're going to keep things as is and continue on. So with all that said, that is where I'm going to stop this video. Thank you guys so much for watching and following along. I hope you're enjoying and learning from the series. And if you haven't already, consider subscribing. Hit the little bell icon there so you get notifications as to when new videos in this or other series drops. Feel free to toss me a thumbs up, a like, or go ahead and hit up the Discord server. Yeah, I will see you guys in the next one.